Hey everybody, we're in the last lesson in Unit 4. We're looking at L'Hopital's rule. It's a great tool when you need to find limits that are really difficult to evaluate. It can also help us with determining limits at infinity and asymptotic behavior. We will use it for curve sketching in the next chapter. And when we're evaluating limits by direct substitution, you should be aware that there are 7 different expressions known as indeterminate form. In AB Calc, we don't use all of them. We're going to mostly be concerned with 0 over 0, infinity over infinity. The other ones you will see in Calc 2 and Calc 3. Let's think about the limit of a quotient. You know, the limit as x approaches a of f of x over g of x. L'Hopital's rule tells us that when the quotient has an indeterminate form, like 0 over 0 or infinity over infinity at that target number, then we can replace the f of x and the g of x by the derivatives of the quotient of the derivatives. And here is that definition again, formally. So when the numerator goes to 0 in the limit and the denominator limit goes to 0, then you can rewrite the limit as the derivative divided by the derivative at that target number. A little bit of caution here. In order to be able to use L'Hopital's rule, you first have to know that these conditions are met. First of all, the derivative in the denominator can't be 0. If it is 0, then you know the limit's undefined. You can't have any oscillating functions. The limit has to approach a single y value at your target number. And the limit of the quotient can't be infinite. If the limit approaches infinity, then the limit's undefined. So just know those 3 things going into this. Communication in math is a really important skill. We want to turn our discussion to the proper notation and the protocol when we're using L'Hopital's rule correctly on the new AP Calc exam before we practice it. So the proper notation and protocol, in order to use this rule on the AP exam, you have to be explicitly showing that the limit in the numerator is 0, infinity, or negative infinity. You have to state that. And you have to state that the limit in the bottom is also 0, infinity, or negative infinity. You can't just write, let me give you an example. You can't just write the limit as x goes to some number on f of x over g of x is 0 over 0. That's not allowed. Don't do that. Don't do that. You have to do it separately. You may want to state that the limit is indeterminate form because they are either both 0 or negative infinity. Now, as a disclaimer, I'm not a grader, so I can't speak to the grading, but I can just tell you what I've been told. You may want to state that the limit is indeterminate form, so we said that. And then after you explicitly show the top and the bottom are a problem area, then you can say the words, by L'Hopital's rule. I'm going to write the limit as, and go forth from there. So I can write the limit as this statement here. Find the upper limit. Find the limit using the proper limit notation throughout. So you want to be sure you do all of those. And I'm going to model that for us as we go. So the very first thing I always want to do is I want to try by direct substitution. Well, I take that back. Yeah, I'm going to say that. I'm going to try by direct substitution. If I put a 5 in there and square it, multiply 9 times 5, and then subtract 5, I'm going to get 0. So I'm going to try that out first and get 0. Also, I'm going to do the same thing in the bottom. The limit as x goes to 5 on x minus 5 is also going to 0. So once I show explicitly that the numerator and the denominator both go to 0, then I can say I have indeterminate form. It's indeterminate. And I'm going to use L'Hopital's rule. Some people just abbreviate that. I would think that they would take that. Okay? So the proper notation is to write the problem 2x squared minus 9x minus 5 divided by x minus 5 and show that I can rewrite that as the derivative of the numerator divided by the derivative of the denominator. Okay, so this is proper format. Now I can use the limit rules for the limit as x goes to 5. So substituting 4 times 5 minus 9 divided by 1, I have a limit. The limit exists. The answer is 11. Okay, let's go on to example 2. So first thing, I want to try direct substitution. X approaches negative 5 and 4 minus negative 5 minus 3 gives us a 0. And x approaching negative 5 in the denominator will also give us 0. So we can say by L'Hopital's rule, we're going to properly rewrite the problem to say that we're going from the original problem that showed to be indeterminate form, that we can rewrite that as the limit approaching negative 5 for the derivative of the numerator, which is negative 1 over 2 times the square root of 4 minus x, divided by the derivative of the denominator, which is 1. So what we just have this piece here to find our value by direct substitution. 2 on the bottom, 4 minus negative 5. This is square root of 9. That's 3. 3 times 2 is 6. So we have a limit of negative 1 over 6. So it's really pretty simple. It's just following the protocol that College Board wants. Sometimes you have to use L'Hopital's rule more than once. So in this case, we have the limit going to negative infinity on x squared is infinity, and the limit going to negative infinity on e to the negative x is positive infinity. So we have infinity divided by infinity. So that's indeterminate. We're going to use L'Hopital's rule by L'Hopital. We have the limit of the original expression, x squared divided by e to the negative x, can be rewritten as the limit approaching negative infinity, and the derivative of the top is 2x. The derivative of the bottom is negative e to the negative x. So now I'm going to try direct substitution. The limit of the numerator is negative infinity. The limit of the denominator is also negative infinity. So this is indeterminate. I'm going to write this one a different way. We have indeterminate form. We've shown explicitly that the numerator and the denominator tend to negative infinity. So I'm saying I know it's indeterminate form, and that gives me permission to use L'Hopital's rule that shows 2x, I'm going back to the first derivative, divided by negative e to the negative x can now be rewritten to be a second derivative. So the derivative of the numerator is now 2, and the derivative of the denominator is e to the negative 2x. So we have this expression. And again, I'm going to use direct substitution. So if we have 2 over e to the negative x, and this is approaching a very large negative number, then the bottom is growing much faster, and it's huge. So when we divide 2 by an extremely large value, then we're going to get 0 by the behavior of numbers. So direct substitution, this is just my thinking. This doesn't really work. It's just I'm using that to explain. How do I know what happens without a calculator? Because if I take 2 and divide that by some super big number, I'm going to end up at 0. You follow that? Good. Okay, this one's really scary. So the limit at negative 2, who put this on here? This is a mess, is of the x cubed plus x squared minus 8x minus 12. I'm going to call that, let's do a little bit of shorthand here. Let's call f of x
today
this
we're
thing.
In lesson 5. We're going to talk about.
Then we can let the denominator be the other function. So we're going to use a little bit of shorthand. That way we won't have to keep writing things over and over and over. So first things first, the limit as x approaches negative 2 on the numerator is 0. And likewise, the limit as x approaches negative 2 on the denominator is also 0. So we can say the limit of negative 2 for the function f and the function g by L'Hopital's rule. L'Hopital's rule can be rewritten as the derivative 3x squared plus 2x minus 8 divided by 3x squared plus 16x plus 20. Now, the limit as x approaches negative 2 on the derivative of the numerator goes to 0, and the limit as x approaches negative 2 for the derivative on the denominator also goes to 0. So we can say the limit going to negative 2 on the derivative of f divided by the derivative of g can be used by L'Hopital's rule and rewritten as the limit going to negative 2 on the second derivative. Second derivative is 6x plus 2, and second derivative is 6x plus 16. So now we have second derivative here. What happens with second derivative? Well, when we put 6 times negative 2 plus 2 and divide it by 6 times negative 2 plus 16, we end up with a number. Negative 12 plus 2 is negative 10, and negative 12 plus 16 is 4, and we have a limit. You don't have to simplify, you don't have to reduce. Actually, you don't have to do anything but do this unless it's a multiple choice question and you're looking for an answer. The AP exam readers would take that work as a valid answer. If you added up and added it wrong and maybe got a 5 here, you're totally wrong. But if you left it there, full credit for that. How about a little trigonometry and transcendental functions? So sometimes these can be a little trickier. This is where, was it back in chapter 1 where we had the trig limit laws? You can see that we could rewrite this using those rules. The limit as x approaches 0 of sine of x divided by x. I'm going to break up this x squared on the bottom and multiply that by the limit as x approaches 0 of 1 minus cosine of x divided by x. If you chose to memorize those two rules, you could be done. And this would be 1 and this would be 0, and 1 times 0 would give you a limit of 0, and you're finished. But let's say you're in a panic and you don't remember that rule, and that looks really scary. In that case, we could say that the limit, and again, I'm thinking about protocol here, the limit of the sine of x times 1 minus cosine of x. So the numerator is going to 0. And of course, the limit on the denominator is also going to 0. So if you use that approach, you've shown that it's indeterminate. And by showing that we have indeterminate form, then we're permitted to use L'Hopital's rule. And L'Hopital's rule says that we can break that problem up and rewrite that as any way we want. The sine of x over x, and let's see, how was it written? I take that back. I think I want to write it a different way because I'm going to pretend like I don't know. It was x squared, sine of x times 1 minus cosine of x. Okay, that's going to get a little ugly taking the derivatives of the numerator and so forth. But we could do that. Just don't feel like I want to do that. So let's do it this way. We could break that up. Keep all of that there. And then pull the other one off, 1 minus cosine. And show that this could be rewritten using L'Hopital's rule as the derivative of sine is cosine, and the derivative of x squared is 2x. The derivative of 1 is 0, and the derivative of negative sine is positive cosine. And then we could try again. So this one, by direct substitution, the cosine of 0 is 1, but the cosine but 2 times 0 is 1 over 0. So we have a does not exist property here, right? And then the limit going for sine at 0 would be 0. So we got 0 times some undefined thing. And that's not very pretty. So we want to rethink that. And remember, I'm playing devil's advocate here. So I'm thinking about if I was some panicked test taker and didn't know what to do, I might go back and rethink that. So the derivative of cosine is 1, and the derivative of this would just be 1, and that would eliminate that. What do I do when I have a 0 over a 0 in this case, right? Or a 1 over a 0 in this case. So what can we do now? The limit going to 0 of cosine is 1, and the limit going to 0 of sine is 0. So now I have, by direct substitution, 1 times 0, because the cosine of 0 is 1 and the sine of 0 is 0, and we do have a limit and the limit exists. Whoop. Now it might be fun to go look at the graph of that just so we can verify. So let's take a look at that graph. And that was a sine of x and then times 1 minus a cosine of x, and the whole thing was divided by x squared. So as you went to 0, you can see that the graph is going to 0. So just playing around with it can help you figure things out. Notice how I regrouped here. I didn't like having 2x on the bottom. Didn't know what to do there, so you can go back and regroup. But as long as you're following the format, it's a good tool for getting yourself out of trouble on limit questions at the end of a year when you've forgotten about limits. Okay, same case here. This one is natural log and e to the x, so we're going to look at the limit in the numerator of natural log of x. So natural log of 1, that's 0, minus 1 plus 1 is 0, and the limit of x going to 1 of e to the 1 minus e is also going to 0. So we have indeterminate form. We're going to use L'Hopital's rule. And rewrite the limit going to 1 of natural log x minus x plus 1 over to the e to the x minus e is going to be rewritten as a limit of the derivatives. The derivative of the numerator is 1 minus x, 1 over x minus 1, and the derivative of the denominator is e to the x. Then substituting, we have 1 over 1 minus 1 over e to the 1, so that's a 0 over e, and 0 divided by e is 0. So this one was easier. And then the fourth type of problems is when we get an infinity over infinity. Now, I know you can use the rules from Algebra 2 and Pre-Calc. And you know, if the limit's heading to infinity, all you need to consider is the end behavior model. So we could use the end behavior model as a solution and say that our answer is 9 over 12 or 3/4. But just to practice, let's try using L'Hopital's rule. So we already know the answer is going to be 3/4 or 9/12. And practicing a limit at infinity, we got 9x squared plus 10x minus 3 is unbounded. It's a parabola. And same for the denominator, is also a parabola. So end behavior is up on both sides. This one's up. We have indeterminate form, so we're going to use L'Hopital's rule. And rewrite the original problem as 9x squared plus 10x minus 3 over 12x squared minus 4 can be rewritten to include the limit of the derivative. So 18x plus 10 divided by 24x. Again, it's going to have to be repeated because the limit as x approached infinity on the first derivative of the numerator is infinity, and the limit at infinity of the first derivative of the denominator is also infinity. We still have indeterminate form, So applying L'Hopital's rule again, we can rewrite the limit going to infinity for the derivative of the numerator divided by the derivative of the denominator can be given as a second derivative, and the derivative of 18x plus 10 is 18, and the derivative of 24x is 24. So there's our 9 over 12 or 18 over 24 or 3 over 4, whatever way you want to write it, bounded by that horizontal asymptote at infinity. A couple more. This one has a parabola in the numerator and an e to the 2x and a natural log in the denominator. So I'm going to make a little note about something, not knowing whether you've seen this in pre-calc or not, but you could consider the hierarchy of the functions and their parent graphs. Hierarchy of functions. And we know that 4x squared grows slower than e to the 2x. E to the 2x is much faster. So if you think about that, you would have a small function, a smaller large number in the numerator, and a much larger large number in the denominator. So we could reason through that and the relative rates of growth, and we could know that the limit is going to be 0. But if you don't know that stuff, or you needed to show work, let's say f of x is the parabola, and g of x is the transcendental function, and the limit at infinity for f of x is infinity, and the limit at infinity for g of x is also infinity, so we could use L'Hopital's rule. And by L'Hopital's rule, we would have the limit going to infinity for f divided by g would now become the limit of the derivative 8x minus 3 over the derivative of the bottom 2e to the 2x plus 1 over x, or x to the negative 1. And then by substitution, we have 8 times a large number. We got it again, don't we? We'd have to show it again. So again, we could say the limit at infinity of the derivative is infinite, and the limit at infinity of the denominator derivative is also. So we're going to repeat L'Hopital's rule again and find that the limit of the first derivative divided by the first derivative of the denominator can be rewritten using L'Hopital's rule. The second derivative of 8x minus 3 is 8, and the second derivative of the denominator is 4e to the 2x minus x to the negative 2. So now we're going to try again. What's going to happen? It's that same kind of thinking again, the behavior of numbers, right? You have 8 in the top, and you have this very large number in the bottom. The larger the number in the bottom divided by 8 is going to push you to 0. We saw that earlier. Okay? Number 9. These are a lot of examples. Here's one that's an AP style with a table. So let's say the table shows you a twice differentiable function, and we're going to use the table to find this limit. So first we're going to think about the limit approaching -2 for f of 3x plus 2. Well, 3x plus 2, as x goes to -2, that's -4, so the f of -4 leads us to trouble, and we have 0 there. And in the denominator, simply a parabola at -2, we're also going to end up with 0, so this gives us indeterminate form. That means we're going to use L'Hopital's rule. By L'Hopital's rule, we can rewrite the limit approaching -2 for f of 3x plus 2 divided by x squared minus 4. This is tricky now, be careful. We've got the f prime of 3x plus 2 times the derivative of the inside, so I'm going to put that in front, times 3. And then derivative of the denominator is 2x. So can we substitute 3 times f prime of -4 divided by 2 times -2. Let's go look at the table. F prime at -4 is 8. So 3 times 8 is 24 divided by -4. And we got -6. That was fun. Couple more, 3 more. Here's another AP style. Use the graph shown below to find the following limit if possible, and use proper notation to justify your findings. So what do we know? We know the limit as we go to 3 on g of x, which is over here as we go to 3. The limit's the y value. That's 2. And we know in the bottom, as we go to 3, on x minus 3, the limit is 0. So we can't use L'Hopital's rule on this problem. We know that the limit of g of x divided by x minus 3 at 3 is 2 divided by 0. So all we can say is that limit does not exist. We don't know anymore. We don't even know the behavior to put them together. We just have an undefined limit. 2 more. The differential equation for the curve of h of x is given by this differential equation. Given that h is twice differentiable, and we know the ordered pair 3, -1 is on the function, we want to find this limit. So first things first, let's find the limit going to 3 of h of x plus x minus 2, and that's going to be the h of 3, which is -1, plus 3 minus 2, so we get 0 in the numerator. And in the denominator, we have the natural log of 7 minus 2 times 3. That's the natural log of 1. And the natural log of 1 is also 0. So we have indeterminate form. And using indeterminate form, we can rewrite the limit by L'Hopital's rule. So the limit of the original problem, h of x plus x minus 2 divided by natural log of 7 minus 2x is going to be rewritten using the derivative of the numerator, h prime, plus 1 divided by negative 2 divided by 7 minus 2x. I know slash fractions are bad, but I'm out of room. Okay, and what do we know about the derivative? Well, we'd have to go back and calculate it because we're going to need it here, right? So dy dx at the point 3, at this point 3, negative 1, we would have 9 on the top and 2 minus 1 on the bottom. So our derivative at that point would be 9 at this point. So keep that in mind. We're going to need that here in a minute. So now we can substitute. We had our value for the derivative. Let's write that down. Dy dx is 9. And h prime of 3 plus 1 divided by negative 2 divided by 7 minus 2 times 3. That's going to give us 9 plus 1, because this derivative is 9, divided by negative 2, and this denominator is 1. So negative 5, we have negative 5 for our derivative. I'm sorry, for our limit at 3. And then our last example, we want to find the limit if possible and give a reason for your answer. So this one is a little crazy. If you think about the limit going to infinity of 2 to the x, that's unbounded up. And same thing with our denominator, the limit going to infinity for x to the 99th power is also positive infinity. So we know we have indeterminate form. But here's the issue. You would have to take, if we said, for example, that our first derivative in the numerator, if the numerator is f of x, the first derivative is going to be natural log of 2 times 2 to the x power, and the second derivative would be natural log of 2 squared times 2 to the x power. And if you kept on going, eventually it would be natural log of 2 to the nth power times 2 to the x. So thinking along those lines and doing the same thing for the bottom, if g of x is x to the 99th power, then g prime would be 99x to the 98th, and g to the double prime would be 99 times 98 x to the 97th. And if you follow that logic all the way down to the end, we're going to get n factorial over x to the 0. So when x gets very large, eventually, I'm going to say eventually, for very large x, we're going to get down to the limit going to infinity of the natural log of 2 to some power times 2 to the x divided by n factorial times x to the 0. So what happens here when you follow just the behavior, what happens here is we're going to get infinity in the top, but we're going to get a constant on the bottom. So infinity on the top and a constant on the bottom means that you've got some huge number over a smaller number. And we're going to say that after doing a whole bunch of derivatives to get something like that, then we would have to have a does not exist situation, because 2 to the x will go to infinity at a faster rate than any polynomial. Faster than any polynomial. We could also say it this way by the hierarchy. 2 to the x is greater than x to the 99th power for very large values of x. So to finish it up, we could say the limit going to infinity of 2 to the x over x to the 99 power does not exist. And that's the end of Unit 4.